Hello everyone, welcome to the next lecture of electronic devices. We are talking about MOS amplifiers, transistor amplifiers. More importantly, or more specifically, we are discussing how we can use the MOS FETs to make amplifier circuits. Okay, so we started talking about this. We saw that our MOS amplifier was a MOS FET can serve as a transconductance amplifier. And in order to obtain a voltage amplifier out of it, we can flow that drain current controlled by the gate to source voltage. We can flow that through a resistance RD, and the potential drop across this resistor will be reflected, uh, will be proportional to the changes in the VGS. So that is how we can obtain a voltage amplifier. However, we are taking an output voltage over here across drain to source just to have a common ground in between input and the output. Our changes in the drain current will be reflected by the changes in the potential across the resistor, and that will produce the corresponding changes if we will write down this equation over here, right? So the changes in the IDRD will be reflected in the VDS, and this ID is being changed by changing the gate to source voltage. We also saw this discuss this voltage transfer characteristics in which our input voltage to the amplifier is a gate to source voltage and the output voltage is a drain to source voltage. We saw that when our gate to source voltage is less than the threshold voltage, transistor is cut off. And you can also see when the gate to source voltage is less than the threshold voltage, no channel will be induced. Again, the drain current will be zero. If the drain current will be zero, then your VDS will be equals to VDD. So that is why this is your cutoff region. And as soon as you increase the gate to source voltage above the threshold voltage, a channel will be induced, a drain current will start to flow. As the drain current will start to flow, the product of IDRD will increase, so the negative will decrease more. So your inverse relationship will start to happen. And this, if you remember your ID and VGS, it was a square law relationship. Right, so now it will be an inverse relationship in between ID and the VDS. So that is why you will see that inverse square law relationship as it will decrease. Then we talked about what will happen at a point B. This point B is when our drain to source voltage will become equal to the overdrive voltage. At this point, the transistor will enter into the saturation region. Okay, so we want to make sure that we will operate the transistor in this saturation region or active region in between points A and B. We also saw that this A and B line segment is a non-linear relationship, right? However, we are interested in developing linear amplifiers. So we also saw that if we will kind of operate the transistor, and today we are going to discuss in much more detail, that we need to select an operating point or a bias point or a quiescent point on this curve and then operate the transistor at this point, such that our output voltages should not enter into the cutoff region and or the triode region to obtain a linear amplification. And you can also see the amplification is proportional to the slope here. So the smaller the region of selection or the smaller the changes in the input voltage, the more linearity we will get. Our focus of today's lecture is based on selecting this bias point, obtaining a linear amplification in detail. We're going to talk about that. Okay, so let's start our lecture today. So we are interested in obtaining again a linear amplification, and how we can do that, we need to bias the transistor. Biasing the transistor over here means that we need to select an operating point on this voltage transfer characteristics. So this is our VTC, voltage transfer characteristics, input voltage gate to source, output voltage drain to source. So biasing the transistor means selecting this DC or a quiescent point or an operating point on the curve such that we will get a linear amplification and non-distorted signal. And this is the overall topic of our today's lecture. We're going to discuss in much detail. Again, here's a circuit. Here's a simple circuit, how we are using an NMOS as an amplifier. Right, so we apply a gate to source voltage. This is a DC voltage, and we get a DC output, drain to source voltage, our DC current. right? So we can operate or select an operating point on this region such that we can get a VDS value and we can get a VGS value. This VDS value should be greater than the threshold voltage, and the VDS value should be greater than the overdrive voltage. So we select this operating point in the saturation or the active region of the transistor operation. And then what we will see, in summary, we will see that the changes in this input voltage, the swings or the time varying input components, how those time varying input changes in the input signal to the amplifier will affect the output signal of this amplifier. And we want to make sure that these variation will result in linear amplification. Okay. So the first thing that we do is we bias the transistor, which means selecting this kill point. So the first point in selecting this kill point is to make sure that when you select this kill point, you want to operate in the saturation region. So select that kill point in between A and B. Okay. Right, so we select a kill point in the line segment AB of the voltage transfer characteristics. We will discuss in kind of again and again in this lecture today about this quiescent point or operating point. So the important thing is that when we operate the transistor at this kill point in the saturation region, our DC voltages that we get is VDS and VGS. And the equation for that is this. How this equation is derived, if you will remember, we started with here, right? So this is the basic equation of this transistor, right? So VDD minus IDRD equals to VDS, this equation. And then we ended up putting the drain current equation over here, Kn VOV whole square, or VGS minus VD whole square. We kind of derived this equation over here, right? So this was the equation. Now in this equation, since we are operating the transistor now at this DC point, so rather than have this time varying signatures, we have this DC signatures. So all we did is replace this DC values here in the equation. And this is how we get this equation. Okay. So the point Q is called as a bias point or the DC operating point or quiescent point. Why it is called as a DC operating point? Because this is the point at which we are just operating with the DC voltages, and subsequently we are going to superimpose the time varying voltages on the top of it. Okay, which comes now. So the signal, since we want to operate this transistor as an amplifier by biasing this transistor, so the objective is we wanna achieve an amplification, and most of our signals are time dependent. Right, so what we do is, the first step to do is to select a DC point on the amplification on the voltage transfer characteristics in the saturation region of line segment A and B. We will talk more about it, where to select this point, whether it needs to be closer to the B, whether it should be closer to the A, where it should be, we're going to discuss in more detail. Okay, so what we do is, after selecting this point, essentially what we are interested in is to amplify the input signature. Then this is our input signature, VGS of t, which is a function of time. It's a time varying signal. So we supply that signal at the input as well. So we will put another signal over here, which is a time varying signal, which is VGS of t, right? So this will end up producing another signature. So the output signature of that will be VDS of t. So we are going to get another VDS of t. So anyways, so when we superimpose this time varying input signal that we are interested in amplifying on this DC voltage, the total instantaneous input voltage at the gate terminal that we get is this, right? So this is the VGS of t, instantaneous gate to source voltage. It's the DC voltage of the bias of the quiescent point and the time varying input voltage, VGS of t. Okay, so what will happen? Now let's look at this voltage transfer characteristics in more detail. Okay, so this is where we are at. Again, this is your circuit, right? So you have a VGS, a DC bias point. Then you have a time varying signal, VGS. And this is your instantaneous voltage, VGS of t, which is a summation of VGS of t plus this capital VGS. Similarly, your VDS will also be time varying. It is going to have this VDS, the DC value, plus the small VDS of t, the time varying output. Okay. Now let's look at the voltage transfer characteristics. Okay, so at this characteristics, we select this quiescent point first. The value of the quiescent point is VDS and VDS, which is this value, this VDS and this VDS. And then we superimpose this time varying input signal. Now so this is the quiescent point value. So we're going to draw this line like this, and then we ended up superimposing this signal. So we can also draw these lines and this line. Oh, sorry, yeah, probably. Okay. Right, so we ended up drawing these dotted lines at this time varying signal, right? So if we will now, the output of that signal is, if you can see that the maximum amplitude over here is intersecting here, and the maximum amplitude over here is intersecting here. Now we are starting with this point. Now you can see that we will start from this point. If I have to plot the output curve now, we're going to start with 0.1. So the 0.1 is over here, so we're going to start with 0.1 here, right? And now as we move to 0.2, our 0.2 is here. So what we are doing is we are moving from 0.1 to 0.2, right? And then this is our 0.3, then we move again to 0.3, right? Then we go back. So we ended up finding out this output voltage, right? Okay, so this output voltage, if you look closely, there are two things that is happening to the output voltage. One, this output signal is amplified. We will realize that this amplification is proportional to the slope of this line, which is a voltage gain. We're going to discuss that in detail later. The second important thing to notice over here is that the signal is inverse, right? So as it is increasing, as the input voltage is increasing, your output voltage over here is decreasing, right? And this is due to the inverse relationship of this voltage transfer characteristics. You can also look at that same thing from the equation as well, in between the input and the output. Okay. So the amplitude of the VGS is small enough to restrict the deviations from the quiescent point to a short, almost linear segment of the VDC. Okay, so the take-home message over here is that another consideration of again about the selecting of this cue point. Where shall we put this cue point? And we can put this cue point by selecting the appropriate DC voltages, right? So we can select this cue point such that we want to obtain a linear amplification, and we want to make sure that this output voltages should not go into the triode region, and it should not go into the cutoff region. Essentially, it will not go into the cutoff region, it will be clipped. And over here, it will still go into this region, but it will be a highly distorted signal rather than linear amplification. So the important thing is we want to make sure that we select the quiescent point and also consider the changes in the input voltages of the VGS, the time varying changes, such that the output voltages will not enter or will not move out of the saturation region. It should not enter into the triode region. It should not go into the cutoff region. And the more closer the swing is around this quiescent point, more linearity we will achieve. Because again, this is a squared law relationship, right? So, however, the more closer we operate to this at any point, we will get a much more linear amplification. Okay, and this is, we just talked about the shorter the line segment, the greater the linearity is achieved, and the closer to an ideal triangular wave that we can develop. So this is the essence of the linear amplification of the MOSFET, right? So the first thing that we do again is we select this quiescent point. Again, selection of this quiescent point should be in the saturation region. Saturation region is in between these points A and B. Second, in order to select this quiescent point, we want to make sure that, so the selection of this quiescent point is important because we want to make sure that the variations of this signature is going to produce the variation of the output signature, right? So our output signature should not enter into the cutoff region and or the triode region. If it will enter into the cutoff region, the transistor will turn off and the voltage will be clipped. If it will enter into the triode region, the transistor will not be off. The current is flowing, but the relationship is very nonlinear. So we're going to get a highly distorted signal. Okay, so let's discuss these 2 points in more detail now. So what is the allowable signal swing at the output? Right, so the first thing that we did is selected the quiescent point. Now it is operating in the saturation region. Okay, great. So what is the signal swing that is allowed in the input and the output? And this is what we have been talking about so far, right? So what will happen when there will be larger changes of the gate to source voltage, right? Okay, so let's look at that. Yeah, if I will just clean this up more. Sorry. Okay. Okay. So first, let's see what will happen as we get more or increased output swings, right? So let's assume that now this is again our DC bias values. Now our, however, voltage swing is going to be very high. Our starting point is still this, but now our, so I'm going to have a different time varying signal which goes all the way from here to all the way from here to all the way from here. Now if you realize that this input signature is entering into this cutoff region. So this was the cutoff region. AB is the saturation region, and this is the triode region. And this is also entering over here in that triode region. So when our signal voltages become very large, so one important thing, two important things. One, even when to obtain the most linear amplification, our voltage swing should be very close to the quiescent point and should be very smaller. Then we will obtain the maximum linear operation. However, even within saturation region, within even AB, if I am operating over here to here, you can see more non-linearities here, right? So even if we have a slightly larger signal, larger voltage swing, while still operating in the saturation region, we are going to see some non-linearities. Now the third case, when we go beyond this saturation region. Now what will happen to this region? What will happen to this input signal when we apply this input signal at the gate terminal? Looking at this input signal at the gate terminal, we know that it is less than the threshold voltage. This means that no channel will be induced, and the output voltage at the output over here will be over here it will be cut off. It will be equal to VDD. Okay, now as it will move from point A to point B, we will see the amplification. We're going to see the amplification all the way to this point. But what will happen to this region, in which it will enter into the triode region? When it will enter into the triode region, the for a larger voltage swings, positive voltage swings for the gate to source voltage, for example this, when this is much more higher, what will happen is our output VDS transistor will enter into this triode region now. However, when it will enter into this triode region, you will realize that our amplification is non-linear, right? So our amplification will drop a lot. So rather than getting this to be amplified like this, our amplification can be very small. And then we will go back. And again cut off and then go back. So two things are happening here. So the one is for the negative voltage swings of the input voltage, when our input voltage has a larger negative swing. So this is the negative swing of the input voltage, right? So whenever there is a larger negative swing of the input voltage, so our VDS is the input voltage, right? Okay, so for a larger negative swing of the input voltage, our output voltage will be clipped. And for a larger swing of the positive peak, or a larger positive swing of the input voltage, which is represented by this, right, our negative peaks of the output voltage will be very distorted, will be heavily distorted by the nonlinear operation of the transistor. So that is why it is important to find out what is the allowable signal swing that is allowed. Okay, so we will discuss this point one more time shortly, so it will be more clear. Okay. Sorry. Okay, so for a larger input voltage signal, the instantaneous operating point will no longer be confined to the linear segment of the VTCs, and this will deviate from the ideal triangular shape and exhibit nonlinear operation, right? So this is what we just talked about, that even in the saturation region, if you have a larger voltage swing somewhere that will lie somewhere over here and here, you're going to start to see some sort of a distortion, or a distortion from the exactly linear amplification. However, what will happen when the signal will become even more larger, when the signal amplitude becomes sufficiently larger now, right, then our operating point may leave this AB line segment altogether. Now our operating point may leave the saturation region entirely. So what will happen is, so we can see that again, when our, for a very large negative swings of the input voltage, our input voltage is VDS, this is our input swing. For the negative, for a very large negative swing of the input voltage, especially when it falls below than the threshold value, our transistor will be off and the output voltage will be equal to VDS, so it will be clipped. Our positive swing will be clipped. And similarly, for a very large positive swing of the input voltage here, right, our negative peak of the amplifiers will be distorted and will be very heavily non-linearly distorted. And another important consideration is this inverse relationship, right? When the larger negative swing of the input voltage is clipping off the positive swing or the positive peak of the output voltage, and the positive swing of the input voltage is distorting, not clipping, distorting non-linearly, heavily non-linearly, the negative peak of the output voltage. And why do we have an inverse relationship? Because of this curve. Okay. So for the negative, when our negative peaks of the input voltage, if we have a very large swing happen at the negative peaks, the transistor will be cut off, and the output positive peaks of the output voltage will be clipped, right, because of the inverse relationship. Similarly, if we, for a very larger swings of the positive peaks of the VGS or the input voltage, the transistor will enter into the triode region and our signal will be heavily non-linearly distorted, or can potentially become flattened. Right, okay, so the important thing is, again, understanding two important factors. One is selecting this quiescent point and understanding the voltage swing. We want to make sure that we will select the quiescent point such that this voltage swing of the input voltage will remain in the saturation region. Okay. So let's find out the value of this small signal voltage gain. Right, so you can consider again this amplifier shown over here in this figure. So in order to find out the small signal voltage gain, we are gonna assume that our VDS, this time varying signal that we are interested in amplifying, is very small. So the corresponding signal at the output is VDS, which will be linearly proportional to VDS. So how we are saying that is because of this curve, right? Is because of this curve. So if we operate this quiescent point and we operate the transistor for a very small changes in this VGS, for very small changes in this VGS, our output will be linearly amplified. Okay, so we're gonna assume that, and the amplification will be equal to the slope, right? So our output is VDS, our input is VGS. So for very small changes of the VGS, we get linear amplification of the VDS, which is equal to the slope, right? So this is equal to the gain. Okay, so our amplification will be proportional to the slope of the line segment of the VTC. Right, so in order to find out the voltage gain of an amplifier, we should find out the slope of this tangent at the quiescent point. Since it's not a linear relationship, and it's a square law relationship, so we have to select a quiescent point. After selecting this quiescent point, in order to find out the slope, what we do is we make a tangent to this point and then find out this changes in the VDS to changes in the VGS. All right, right. So, okay, so this is the voltage gain. So this is the finding out the slope of this voltage transfer characteristics, output, input at quiescent point when the VGS is equal to this DC value of the VDS. So here's the equation, right? So if you will take a derivative with respect to VGS, what you're gonna get is something like, so this will be 0. You're gonna get minus half kn RD square VDS minus VT, so 2 so it will be minus kn RD VGS minus VT is VOV. So this is the amplification of the amplifier, linear amplifier, or a small signal voltage gain when we will obtain the linear amplification. Right, so this is the same as that what we find out, and this VGS minus VT is the overdrive voltage, so we ended up getting this linear amplification. So important thing over here, again, note that the amplification is inverse or inverted or 180 degree phase shifted, and it is directly proportional to the value of the load resistance, the overdrive voltage, and the transistor cross conductance parameter. Okay. So let's also try to represent this or evaluate equation for the voltage gain in terms of the drain current that is flowing through the transistor. So we know that for the DC current in the saturation region of an MOS equals half Kn VOV whole square. So this is the drain current equation for the NMOS when it is operating in the saturation and or the active region. So in order to find out the gain value in terms of the drain current, we will take this equation again. AV equals minus Kn VOV RD. Oh, sorry, okay. Right, so this was our equation. So what we will do is we are going to replace this value of the Kn from here to here, right? So the value of the Kn over here is 2 times ID over VOV whole square. So replace this value over here and we can find out this equation. So it will be minus ID RD over VOV, half of VOV. So now we can, this is kind of another relationship for the small signal voltage gain, that our small signal voltage gain is proportional to the drain current, the value of the load resistance, and the overdrive voltage. Okay, so we can also alternatively write it as, we know another equation, right? So we know that VDS was equals to VDD minus IDRD. So we can replace this IDRD by VDS minus VDD, right? Okay, right. So we VDD minus VDS. So we ended up replacing this IDRD for using this equation by VDS minus VDD minus VDS. And so this is another relationship of the voltage gain that is shown in terms of the drain to source voltage or the output voltage, and the overdrive voltage. Overdrive voltage again so this is the output voltage, right? And overdrive voltage is VGS minus VT. So this is the input voltage. Okay, so this is a small signal voltage gain. Okay, so another important concept over here is to find out what is the maximum value of the amplification that we can achieve using these voltage transfer characteristics. So here is the voltage transfer characteristics. If you look closely at this characteristics, or in the saturation region, the maximum amplification will be achieved at point B because the slope at point B is the highest. So in order to find out the theoretical maximum voltage gain, we can find this out at point B, right? So this is the maximum value of the voltage gain. So this is VDD, this was drain to source voltage, so drain to source voltage at point B, and the overdrive voltage at point B. So we know that the drain to source voltage at point B was equal to the overdrive voltage at point B, right? This was the edge of saturation, right? So since this is equal to this, so we can replace this value over here to find out this equation. Okay, so the concept over here important is, so this is the theoretical maximum value of the gain that we can obtain from the voltage transfer characteristics for a particular NMOS. So the important consideration point is whether it is even advisable to operate the transistor at the point B or not, right? Another conceptual important question. Okay, so what will happen if we will operate the transistor at point B, and there is a voltage swing? Okay, yeah. Okay, so what will happen? So for any smaller positive swings of the input voltage, so if we are operating the transistor at this point, right? So this means that our DC value is this, right? So this is our VGS. So any positive changes over here will end up distorting the negative peaks of the output voltage, right? So our output voltage will become distorted. The negative peaks of the output voltage will become distorted or heavily distorted or will become flattened. So that is why although we obtain the maximum gain at the point B, we will not operate the transistor or the amplifier at a point B just because it is going to distort the negative peaks of the output voltage. So we, however, in order to make sure that we want to get the maximum amplification from the transistor, we will like to operate the transistor at very close to the point B, while making sure that the swings of the input voltage will not distort or clip off the swings of the output voltage. Okay, so where we are at? Okay, right. Okay, so although the operating the or biasing it at a point B is going to provide the highest gain, but there is no room for the negative signal swing at the output, right? This is what we just discussed. So it provides an upper bound, so this will give us a maximum value of the gain, but again we don't operate the transistor at this value because we do not have a room for the negative peaks of the output voltage. It will be distorted. So we operate the transistor, or we select the bias point as close possible to the point B as feasible, while making sure that our voltage swings are allowed. So now we are going to do an example that will shed more light on this voltage swing phenomena and what are the voltage values that are allowed or not. Okay, so let's look at this example. This is a circuit which we have been seeing for a while now. So this is a NMOS transistor amplifier. It is biased at this VGS value. We're going to get a corresponding VDS, and then it's a time varying signal, VDS of t, that we can apply, VGS of t. And then we have a drain current that is flowing over here. In terms of the transistor parameters, this is a threshold voltage, gate to source voltage, process transconductance parameter, aspect ratio, no channel length modulation effect. Okay, so in the first part, what we want to do is we say that, okay, let's find out all of these values, the DC values at the bias point, while assuming this VGS to be 0. So initially we're going to assume it to be 0 and find out all the bias values. So let's start with VOV. What is VOV? So we know that VOV is our overdrive voltage, which is equals to VGS minus VT. VGS is 0.6, VT is 0.4. So we get 0.2. Okay, overdrive voltage is 0.2. The second thing that we want to find out now, right, this is 0.2. The second thing that we want to find out now is drain current. So what is the value of the drain current? So for now, let's assume, now we know that if you remember in all the summary slides in the last chapter, in order to find the drain current, first we want to know in which region the transistor is operating. Since our question did not specifically say in which region it is an operating, but just said that it's an amplifier circuit, it's fair to assume that it is operating in the saturation and or the active region, right? However, we can still make an assumption that it is operating in the saturation region, and we should verify that it is actually operating in the saturation region as well. So let's start with this. Finding out the drain current such that it is operating in the saturation region. So it should be half Kn VOV whole square. Right. So Kn is Kn dash W over L. So we ended up putting all the values, right? So this is Kn dash W over L. Overdrive voltage is coming over here. So we ended up finding the drain current, 0.08 milliamperes. So we find the overdrive voltage, we end up finding the drain current. Let's find the VDS value. So we know that our VDS should be, where is the DC value of the VDS should be equals to VDD minus IDRD. We know the value of the VDD, 1.8 volts. ID 0.08 milliamperes, RD 7.5 kilo ohms. So we can find the value of the VDS. So value of the VDS is 0.4 volts. So we ended up finding all the values, but before we find the gain, let's also verify our assumption that the NMOS is actually operating in the saturation or active region. One condition for the NMOS to operate in the saturation region is when our drain to source voltage should be greater or equal to overdrive voltage. Our drain to source voltage is 0.4 volts and overdrive voltage is 0.2 volts, right? So this is 0.4, this is 0.2. So indeed it was operating in the saturation region. This was also kind of given in the when it says that it's an amplifier circuit, and we know that we operate the transistor in the saturation region for amplification purposes. Okay, now let's do the final part of this. We need to find out this voltage gain. So in order to find the voltage gain, let's look at this equation. Where did we derive the equation? We derive the equation over here. So this is the equation of the voltage gain, which is minus Kn VOV RD. Right, so voltage gain is minus Kn VOV RD. So all the values are given, right? So we have an RD 17.5, VOV 0.2 again. Kn is Kn dash into W over L, and then AV. So we can easily find out this value to be minus 14. Note that again, your voltage amplification, it comes with a negative sign, which means that it is inverted. Okay, so let's do the second part of this problem now, which is what is the maximum symmetrical signal swing allowed at the drain, right? And again, the drain is this drain, so this means that output signal. So what is the maximum symmetrical signal allowed? Always read the questions very carefully. All the important words are there. Another important thing is that we wanna find out the maximum swing that is allowed for the linear operation, and the second is it should be symmetrical. Symmetrical means, right, so the negative and the positive swing should be the same and allowed. Okay, so in order to find that out, so let's go over here. So we know that at our Q point, we ended up finding our drain to source voltage is 0.4 volts and our gate to source voltage is 0.6. So let's find out what is the maximum symmetrical swing allowed. Again, this is a generic characteristics of the curve. So let's assume that we are operating somewhere over here where our VDS value is equals to 0.4 volts and our VDS value equals to 0.6 volts. So we want to make sure that we want to find out what is the positive and the negative, what positive over here and what negative over here is allowed and symmetrical. Okay, so let's start with the negative swing. Okay, so let's find out what is the negative swing allowed at the drain or the output voltage. How we can find out? We know that we don't wanna operate the transistor in the cutoff end or the triode region. This means that I don't want to move away from this point B, and this point B is equals to the overdrive voltage, right? This is the edge of saturation region when it moves from the saturation to the triode. And for an NMOS, we know that this happens when the drain to source voltage is equal to the overdrive voltage. So what was the value of the overdrive voltage? Our overdrive voltage was 0.2 volts. So this was equals to 0.2 volts. So this means that the negative swing that is allowed from here to here is 0.2 volts. So 0.4 minus 0.2 equals 0.2. So this is the current quiescent point. So the maximum VDS that is allowed is the difference in between the quiescent point voltage value and the overdrive voltage value. So it should be 0.2 volts. Now let's find out what is a positive symmetrical swing allowed or not, right? So in order to find out the positive swing and the symmetrical swing, we know that, so the one thing is that we know that we cannot go beyond 0.2 volts for the negative swing, right? So this means that first what we will do is we will check whether 0.2 volts will be allowed as a positive swing or not. If it is not, then we will change the negative swing because we want to find out the symmetrical swing, and then make sure that whatever the swing that we will find out, it should be symmetrical and allowed. So for the negative, we ended up finding out 0.2. So let's check whether the 0.2 is also allowed or not. So what will happen at 0.4 if I will add 0.2 this 0.4? What is the value of the VDD? VDD is 1.8 volts. So this is 1.8 volts. So if I will add 0.4 another 0.2 volts here as a positive swing. So the value of the voltage that I get for the VDS is 0.6, right? Since this 0.6 is still less than 1.8 volts, so of course it is allowed. We have a much higher positive voltage swing allowed, but since we are interested in finding out the symmetrical swing, so that is why it is also 0.2 volts, plus minus. Right, since 0.6 is very less than VDD, so it is allowed. Even VDS greater than that is also allowed, but we are interested in finding out the symmetrical swing that is allowed. Okay, so what is the other thing that we want to find out? The other thing that we want to find out is what is the maximum amplitude of the sinusoidal VGS, right? Now we know that, now we find out that, okay, the maximum symmetrical swing that is allowed is plus minus 0.2 volts. Well, we want to find out that what is the maximum amplitude of the VGS that is allowed, right? So we ended up finding out, so these are for the positive, for the output signatures or the VDS signatures that are allowed. Now we want to find out that what is the swing at the input voltage that is allowed, right? So in order to find out the input signatures that are allowed, we can easily find out by, we already know the voltage gain. And so if I will write it in very simple words, it should be output over input. Right, so we know the value of the voltage gain, we know the value, the signal allowed at the output voltage, so we can find out the signal allowed at the input voltage from here, right? So here's the equation. So here's our input voltage, VDS, here's our output voltage, and here's our voltage gain. We are just taking the modulus value, keeping things simple here. Right, so you can also do this thing over here. So VI equals minus V naught over AV. If you take a modulus, then you don't need to worry about this negative sign. Right, so this is the symmetrical swing allowed at the output, the gain. So 14.2 millivolts will be the value of the negative swing that is allowed. Notice the difference, right? So we have at very small changes of at very small signal swings of the input voltage, we can obtain a linear amplification at the output. Okay. We can also do this alternatively using another approach, kind of a graphical approach. So look at that over here to find out what is the maximum voltage swing that is allowed, or what is the maximum input value of the VGS that is allowed. So here is the gate to source voltage, right? So this is the DC value of the gate to source voltage, and this is that time varying signature on the top of it, right? So if we will write this, if this is VGS, then this is the equation for this maximum value of the VGS, which is VGS max equals to VGS, the DC value, plus the time varying component. And similarly, our drain to source voltage, which will be the amplified inverse amplified waveform of the input voltage. So that is why you can see that it is inverse and it is amplified. This is the DC part of that curve, and this is the time varying component. So the minimum value of the minimum value of this can be written as VDS minus the negative peak VDS. So how we can find out the value of the maximum value of the VGS? So what we were interested in is finding out we were interested in finding out the maximum value of the VGS that is allowed. So now we are trying to do this thing graphically. So here's the condition that we can use in order to make sure that our transistor will operate in the saturation region, right? In order to make sure that our transistor will operate into the saturation region, we want to make sure that the maximum value of the VDS should not fall below here, right? Okay. So the minimum value of the VDS should not fall below here, right? So this is the output voltage VDS. So the minimum value of this VDS should not fall below, otherwise it will enter into the triode region. So we want to make sure that in order to make sure the MOSFET is operating in the saturation region, the VDS minimum value should be greater than your overdrive voltage. Right, okay, so this can also be written as like this, or greater or equal to, for the saturation region operation. Okay, so VDS minimum should be greater, and we know that overdrive voltage is gate to source voltage minus threshold voltage, so this should be maximum of this, right? So we ended up writing this down: VDS minimum, VDS minus VT over here. Now we know that VDS minimum equals to VDS minus VDS here. So we can replace this VDS minimum here, and similarly we can replace this VDS max over here. So we get a VDS minimum is the DC value of the VDS, which is 0.4 volts, minus the VDS. So this VDS is essentially, we know that mod of AV is VDS over VGS. So the VDS over here is the gain into VGS. So we ended up replacing this over here. Similarly, VGS max can be written as the DC value of the VGS, which is 0.6, plus VGS, this value, and minus threshold voltage, minus 0.4. So if you will solve for this equation, you can find out this value of the VGS to be equal to 13.3 millivolts. We already know all the components over here. We know that the maximum value of the we already know the voltage gain, which is equals to 14. The mod value of the voltage gain is 14. So if we will use that value, our voltage swing, our maximum value of the VGS, that will come out to be around 13.3 millivolts, right? So it should be, so the positive swing, or the maximum positive swing that is allowed in the gate to source voltage or the input voltage should be less than 13.3 millivolts. Now you can note down that this value is very close to the other value that we find out by numerical analysis, 14.2. So you can do it either way. Now we have one more quick topic, and then we will finish our lecture. So we can also find out, we can also kind of determine or operate the transistor at a specific kill point. Rather than using the voltage transfer characteristics, we can use the IV characteristics of the NMOS. Okay, so here's an IV characteristic of the NMOS, right? So this is the VDS, this is the ID. We will see that as we increase our drive voltage, we can get the square law relationship. So this is, right, so this is a square law relationship over here. This is a triode region, this is a saturation region. We have seen this thing like so many times by now. So important thing on this plot is this load line. So let's draw this load line. What does this load line represent? So we know that for our transistor that we have seen for amplification purposes, right? For example, even this one, this is the one that we have been seeing forever now. Okay, so our equation was something like VDS equals to VDD minus ID RD, or you can also write as ID equals VDD minus VDS over RD. Now let's plot this line, this load line. So how we can plot this load line? So the first thing is, so when ID will be 0, so right, for example, when this ID will be 0, the VDS is equal to VDD, so we get this A point. And now as the drain current is increasing, right, so as we increase this drain current, as this drain current will increase, our or you can also think it the other way. If we look at this equation, as our drain to source voltage is decreasing, right, so if we will decrease the drain to source voltage, our ID will increase, right? So we can kind of get this inverse relationship in between our drain current and the drain to source voltage, which can also be seen from here, right? So our ID equals to 1 over RD into VDD minus VDS. So we have an inverse relationship in between the VDS and ID, and it's an inverse linear relationship. So that is why you get this linear line. Sorry. Okay, now let's look at all the specific points. Okay, so before actually we go to the talk about this point A, Q, B, and C, let's find out why the slope of this line is minus 1 over RD, right? So how do we define the slope? We know that in order to define the slope, we can take the slope by taking a derivative So the slope of this line is the so derivative of ID2 with respect to the VDS. So if I take this one, so I will get 1 over RD. So this will be 0, VDD will be 0, and minus VDS will be minus 1. So this, right? So the slope of this line, this load line, ID over VDS, will be equals to minus 1 over RD. So this is how we find the slope of this line. Okay. So before discussing these points, we will discuss this, all of these A, B, C, E, and Q points shortly. Again, this plot is the ID VDS graph. And what we are trying to do over here, we can also see that using this graphical analysis, we can also find out the quiescent point, or we can locate the find out the position of the kill point where we can operate the transistor as a linear amplifier. This is the equation that we just derived. We also find out this value of the RD, which can be find out by taking a slope of the load line. Right, so this is RD is a load resistance, so that is why it is called as a load line. Another important point over here is this point A represents VGS is equal to VT, right? So you can draw one-to-one kind of a similarity in between this graphical characteristics and the voltage transfer characteristics. If I will go back to this A point on this characteristics was here, right? And at this point, you can see that the gate to source voltage was equal to the threshold voltage, right? And your drain to source voltage was equal to the VDD, right? So your drain to source voltage is equal to VDD, and your gate to source voltage is equal to the threshold voltage. Okay, so the kill point is this quiescent point where we operate the transistor. So in order to again operate the transistor, we saw that our VGS should be equal to this DC value, and VDS would be equals to this DC value. Our B point over here, we can easily see that this is a point of intersection, or this is a point of edge of the saturation region. This is a point in between the saturation region or the triode region. And then our point C is deep in the triode region. So the condition of the saturation region, we kind of discussed this multiple times now, that our drain to source voltage should be equal to the overdrive voltage. Right, and the C point again is deep in the triode region. We will also shortly realize that we can use these points A and C to operate the transistor as a switch. Okay, so let's very kind of in a couple of minutes, let's talk about this switch thing. So at point A, in order to, we have been talking about this transistor, operating this transistor as an amplifier, and that is the main focus. Again, we are going to discuss this continuously. So very briefly, just looking at these characteristics, we can operate the transistor as a switch by operating the transistor in between A and C point. We also touched upon this basic concept in the chapter number 5 while talking about the MOS FETs, that in order to operate the transistor as a switch, we need to operate that in the cutoff region as an off and an on in the triode region, right? And for the saturation region, when it is operated in the saturation region, we can operate that as an amplifier. Now the same thing is true over here. At point A, it is cut off, and at point C, it is in the saturation region. Another thing to realize over here, at point C, our slope is very high, right? Our slope at the point C is very high. So this means that our resistance is very low. So if we operate the transistor as a switch, right, we want to have a very low resistance. Okay. So MOS FET can be operated as a switch by operating it in between points A and C. At point A, the transistor is cut off, or so it's an open switch, which can be represented by looking at this. When our gate to source voltage is less than the threshold voltage, transistor is cut off. However, at point C, when it is deep in that triode region, we can see that the resistance of this curve is very small, right? So we want to have a low resistance. So the voltage drop across the switch will be very low. So this will become a closed switch. However, there is a slope and the resistance is small, but there is a resistance. So that resistance is known as this closure resistance for the switch. Okay. And also note that the value of the VDC at the point C is also very small. At this point C, if we go over here, the value of the VDC is also very small. So while operating the transistor as a switch, we operate that in between points A and C, which are the cutoff point and the triode region operation. And we operate that in the triode region because the resistance values are very small, so the voltage drop across the output will be very small. So however, there will be a voltage drop across the output, albeit small. So that resistance that will appear over there is known as the closure resistance. Okay, so this is kind of a very quick thing that we want to again introduce over here. Now going back to the amplifiers main topic of our course, going back to this curve again, we will now see that where to select. Again, we have been talking about selection of this quiescent point for the proper operation of the transistor as a linear amplifier, and while allowing the swings of the input and the output voltages without being cut off or without being clipped or distorted. Okay, so looking at this plot again, we will see that how to find out the right quiescent point. Okay, so here is a couple of quiescent point, a couple of load lines drawn, in which one quiescent point over here and the other quiescent point over here. So let's find out what are the advantages or the disadvantages of each quiescent point. Now we can see that this Q quiescent point is very close to the cutoff, right? So this was a cutoff point. This was a point A, cutoff point. So this quiescent point is very close to the cutoff. So this means that if we will operate the transistor at this quiescent point, right? So the problem that we will run into, if there will be any negative swings, our larger negative swings in the input voltage is going to clip the positive peaks of the output voltage, right? Because this quiescent point is very close to the cutoff. So we can draw the similar comparison over here by looking at this voltage transfer characteristics. If our quiescent point will be over here, very close to the point A, then any smaller negative peaks would end up clipping the output voltages. Now the similar comparison is drawn for the Q2 point, right? So this is, by the way, what we just talked about. So the similar comparison is drawn for the Q2 point. The Q2 point is very close to the point B. The point B was somewhere over here. It is very close to the point B. This means that any larger positive swings of the input voltage is going to heavily distort the negative peaks of the output voltage, which is very similar to selecting a quiescent point over here, Q2, and this is Q1, right? So if we will select a quiescent point over here, Q2, so any positive swings will enter the transistor, will enter the output into the triode region, and we will get a very heavily non-linear distortion and the flattening of the negative peaks of the output voltage. So that is why finding the selection of this quiescent point, whether on the voltage transfer characteristics or IV characteristics of the MOS transistor, is very important. And the things that we should consider is essentially 2 or 3 things. The most important thing that we should consider, two important things, right? So the first thing is, what is the gain value that we want? And we already discussed that the gain will become more and more or very close to the point B. So the more closer we operate the transistor at the point B, the more high gain we will achieve. However, having said that, the second important consideration is the desired voltage swing. We want to make sure that while we operate the transistor, we do consider the voltage swings that are allowed. And in order to find that what are the voltage swings that are allowed, the most important consideration is we want to make sure that our output voltages will not enter into the cutoff region. Otherwise, the output voltage will be clipped, or it will not enter, or its negative peaks will not enter into the triode region. Otherwise, its negative peaks will be heavily distorted. It will not be cut off because we still have a drain current that is flowing. It will be heavily distorted and can potentially become flattened. Okay, so with that, I am going to end our lecture today. Today, we kind of discussed in more detail how to obtain a linear amplification and how to select a quiescent point on voltage transfer characteristics and the IV characteristics of an MOS transistor. Okay, so with that, thank you so much. We will talk in the next lecture about the small signal operation, and we will also discuss different configurations of MOS FET amplifiers. All right, thank you so much. Have a good day. Bye bye.